The International Space Station has a date to die. The largest structure humanity has ever assembled in space already has a date to fall. This isn't drama, it's the official plan. NASA will bring the ISS down over the Pacific. Now you'll see how, when, and why this needs to happen. The ISS is an achievement that defined an era. It was born from the union of goals, resources, and engineering from several countries, turning a bold idea into a stable scientific infrastructure about 400 kilometers above Earth. Construction began in 1998 and, over the years, involved the coordinated work of at least 15 nations to maintain a permanent laboratory in space. In this microgravity environment, experiments that Earth's gravity would prevent become possible. Much of what we understand today about human physiology in space, materials, combustion, fluid dynamics, and orbital instrumentation comes from results gathered there. Life on board is intense. In 24 hours, the station completes approximately 16 orbits around the planet. For those inside, that means watching several sunrises and sunsets per day while conducting studies that range from biology to medicine, from physics to flight technology. And this routine has never been interrupted since the year 2000. From then on, there has always been someone occupying the most remote outpost humanity runs continuously beyond Earth. In size and mass, the station impresses. It is about 108 meters long, with a width to rival a stadium, and more than 419,000 kilograms counting pressurized modules, trusses, radiators, systems, external equipment, and solar arrays. None of this reached space ready all at once. The ISS is modular. It was assembled piece by piece, like a huge three-dimensional jigsaw puzzle. Each element was designed to dock to the others with precision, following international standards that allow hardware from different agencies to work as if it had been built in the same place. That strategy made the logistics viable. Over many years, dozens of missions delivered components to orbit. NASA's retired space shuttles carried modules and robotic arms. Russian rockets placed segments and resupplied the crew. Cargo spacecraft from Europe and Japan delivered supplies, experiments, and spare parts. In orbit, astronauts performed spacewalks and docking maneuvers to secure each part in the right position. The result is a unique platform where technologies from multiple countries integrate, generating scientific productivity none of the participants could have achieved alone. The station has already hosted visitors from 20 nations, consolidating its role as a showcase of cooperation in an extreme environment. Beyond data and discoveries, there is powerful symbolic value. Different cultures and languages sharing the same laboratory, the same recycled water, and the same filtered air for a common purpose. When we look up at the ISS gliding over our cities, that spirit of collaboration shines too. So why end a project of such relevance? The answer blends engineering, safety, and long-term planning. NASA intends to end operations around 2030, completing about 3 decades of uninterrupted occupation. It will not be a sudden shutdown. It will be a phased, planned process, with the goal of guiding an object of more than 400 tons to a controlled re-entry, far from populated areas. The final destination has a name and coordinates: Point Nemo, the most isolated region of the Pacific Ocean. To get there, the station will go through a sequence of orbital adjustments. First comes the natural descent phase, when the very subtle drag from the upper layers of the atmosphere steals velocity and gradually lowers the altitude. Then, when it reaches the ideal range for the final maneuver, a dedicated deorbiting vehicle, docked to the ISS months before the last operation, comes into play. The function of this spacecraft is to apply trajectory corrections and the final push that puts the station into the calculated atmospheric corridor to burn up over the chosen ocean. Re-entry is not a disorderly fall. It is a sequence of timed commands and burns. As it touches denser layers of air, friction generates temperatures that easily exceed 1,500 degrees Celsius. External structures, Panels, insulation, and much of the pressurized modules disintegrate. Some tougher pieces, such as tanks and dense structural components, may survive part of the heating and reach the ocean as debris. That's why target precision is so important. Steering re-entry to an extremely remote region reduces the risk to practically zero for the population. This process comes with expected effects. The heating creates a plasma cloud around the fragments, shock waves, and trails that can disperse along slightly different paths. The solution is to monitor the re-entry window in real time with telemetry and modeling to refine guidance right up to the final moments. The margin for error is small, so coordination between ground teams and the station's own systems is essential. Another critical point is the evacuation schedule. Weeks before the final phase, the last crew leaves the laboratory. From then on, all control is done remotely. Ground controllers adjust attitude, pointing, mass distribution, and prepare the deorbiting vehicle to execute the final sequence. This ensures no one is exposed in the orbital environment during the most delicate weeks. If the decision is so technical, what drove the outcome? Over nearly 3 decades, even with rigorous maintenance and cleaning protocols, the internal environment accumulates wear. Microorganisms that came in on clothing, supplies, and from the human microbiota find niches where they can take hold. Particles released by equipment and materials that slowly degrade in microgravity create ongoing challenges. Structural items age. Seals and connections require constant inspection. Redundancy keeps everything safe. But there comes a point when the effort and cost to guarantee reliability and habitability rise sharply. In parallel, ground infrastructure, support spacecraft, and logistics contracts must evolve. And it is necessary to free up budget and focus for the next stages of human presence in space. There is also the responsibility of end of life. Leaving a structure of this size aging in orbit until a failure causes an unpredictable re-entry is not acceptable. Controlled deorbit is the safest way to end the life cycle of such a large satellite. It avoids surprises, reduces risks, and shows that it is possible to manage the end of a mission responsibly. Does this mean the end of space stations? No. It means the end of a generation. The ISS paved the way for the continuous presence of humans in orbit and served as a school for those designing the next platforms. New laboratories, public and private, are likely to take on the role of hosting research and technology testing with more modular approaches, simplified maintenance, and costs shared among commercial partners. The experience accumulated in docking vehicles from multiple origins, in energy management, in water and air recycling, and in crew health will be applied to new habitats, including in higher orbits, as support for lunar missions and, in the future, for longer journeys. Before the farewell, it's worth recapping what this station has delivered. We learned to grow plants where roots don't know which way to grow. We observed how muscles and bones behave when they are hardly required, and how to counter those effects. We tested instruments, antennas, sensors, and materials that now equip satellites, telescopes, and probes. We saw how fluids mix without the push of weight, how flames propagate without convection, and how tiny forces, negligible on Earth, dominate the behavior of liquids and particles in microgravity. All of this while different countries rotated crews, shared data, and aligned procedures. It's natural to feel a lump in your throat thinking about the ISS's last orbit. How many times did we look up, follow its bright streak, and feel that, for a few minutes, there was a human home passing over our heads? Ending well is part of the cycle of any major project. The station's planned end is another chapter in the maturation of space exploration. The same competence that raised, expanded, and operated this laboratory for decades will guide its farewell with safety and precision. When the deorbit sequence begins, there will be no audience on board. The station, silent, will obey the final commands, adjust its pointing, and, guided by the final push, dive into the re-entry corridor. Down below, in control centers and at antennas around the globe, engineers will follow every datum and every curve. Most of that colossus of metal, composites, wires, and dreams will become light and heat in the upper atmosphere. What remains will meet the most distant sea of all, and none of this will be a waste. The knowledge remains, the partnerships remain, the road to the next stations and beyond low Earth orbit remains. If this content clarified how the farewell to the International Space Station will unfold, strengthen the channel with your like and subscription. Here, the conversation about space is continuous, just like our curiosity. Thank you for watching, and see you in the next video.